Hello everyone and welcome back to another video. Today we're starting chapter 3, which takes us all the way back to and expands upon a topic that we introduced in chapter 1, and that is congruence. So just for a brief recap, in case you guys forgot what we went over in like one of the very first videos of this series, in chapter 1 we defined congruence as this. Suppose a, b, and n are all integers with n greater than 0. We say that a and b are congruent modulo n if and only if n divides a minus b. And we denote this relationship as a is congruent to b mod n, and that's how we say it. And we read them like a is congruent to b modulo n. So along with that, we proved a few aspects of this relationship, of this relation. First, we proved that it's reflexive. And that's theorem 1.9. And that basically just means a is always congruent to a mod n. Very basic, very simple. And then symmetric. And then that's theorem 1.10. And that just states if a is congruent to b mod n, then b is congruent to a mod n. Additionally, we proved that it's transitive, and that's theorem 1.11, which said if a is congruent to b mod n and b is congruent to c mod n, then a is congruent to c mod n. And all these different things, very similar to equality with all of this. And then finally, last of all, we proved the following properties. So we proved basically if a is congruent to b mod n and c is congruent to d mod n. Using this, we proved three different things. The first thing we proved was that a plus c is congruent to b plus d. And this was theorem 1.12. And you're going to see me reference all of these throughout this video, or at least most of them. Additionally, like subtraction, theorem 1.13, and then finally, I'm doing the same. I'm doing these arrows away from the same formula because I just don't want to write it 3 different times. These videos are long enough as it is, but multiplicative. Basically, all this is saying is like if you add two things that are congruent together, they're going to be like the congruence relationship is equivalent across addition. Similar how to like if you add 1 plus 2 and then 1, and then you also add 1 plus 2 together, they're going to be the same. It's a little bit more interesting in congruence because situations could occur like 1 is congruent to 4 mod 3. In addition, you can basically in mod 3 use 1 and 4 the same, essentially. Treat them as equivalent in addition. And then that also applies in subtraction and multiplication. Not division, though. That's a important caveat. But another one that we proved, so these are the 3 theorems that we proved about addition, subtraction, multiplication. And then additionally, we finally showed also that if A is congruent to B mod n, then A to the k is congruent to B to the k mod n. And that was theorem 1.18, which is basically about taking powers in modular arithmetic, which is actually going to be a super relevant topic all throughout number theory. Like, we'll come back to taking powers in modular arithmetic because it's useful in a lot of different theorems we prove later on. But for now, this is all we know about modular arithmetic. Now, the first thing that we're going to look at, and this is kind of where the book starts, we're going to look at taking numbers to large powers in modular arithmetic. So, and I don't know if you guys can hear my kittens there. He's like clawing at the door right now trying to get in, but I am recording. Sorry. We're doing powers now. So to start, basically the book discusses the process of taking numbers to large powers, modulo n, and essentially it uses some of these theorems and uses theorem 1.18 to essentially break down these large powers into smaller, more manageable powers. Let's look at the first example of this. So the first example, we want to show that 41 divides 20, or sorry, it divides 2 to the power of 20 minus 1. And then basically how that works, so we take 2 to the power of, so basically what they're going to do throughout this, this 2 to the power of 20 is a very large power. Like, that ultimately results in a very large power of 2. So to actually figure this out and figure out whether 41 divides it or not, very like computationally intense process. But what the book does is show us how to solve this power in a way that essentially in mod 41, in a way that allows us to show that this is ultimately divisible by 41. So to begin with, they start by basically showing 2 to the power of 5 is congruent to -9 mod 41. And the reason why that is because 2 to the power of 5 equals 32, which is just 41 minus 9. So that's how I know that. Additionally, 2 to the 5 to the power of 4, basically applying theorem 1.18, we can see that it's -9 to the power of 4 mod 4. And then after that, so what we can do here, we can break apart this 4 into -9 to squared, and then square that. And what that basically does, 2 to the power of 20, so because we can multiply exponents, just basic exponent rules, 2 to the power of 20, and then it's 81 squared mod 4. Okay. So it's 2 to the power of 20 congruent to 81 squared mod 41. And that's basically just because 9 squared equals 81. And additionally, what this means, what is 81? Well, we can take 81 and change it into a different number based on this mod 41. I kept writing mod 4 there. But basically how it works, so you take 2 to the 20 and it's congruent to -1 squared in mod 41. And the reason why that works is because 41 times 2 minus 1 equals 81. So 81 is congruent to -1 mod 41. So finally, what this means is 2 to the power of 20 is congruent to 1 mod 41, sorry. Subtract 1 from both sides, which we can do based on theorem 1.13. So then 2 to the power of 20 minus 1 is congruent to 0 mod 41, which means that 41 divides 2 to the power of 20 minus 1, just by the definition of congruence. So this is so the book continues on with many more examples, and I think all of those are worth looking over if you want to continue practicing this. Just for time's sake, I'm going to move on, and it ultimately leads you to this new method of solving any large power in modular arithmetic very quickly. And this method essentially involves writing a power, or writing a number as a sum of powers of 2. But this method is probably the easiest to describe with an example. So let's go over an example of that quick, just so you can understand what this method is. And we'll just take the rest of this space, honestly. Yeah, because I should have 3 more rows to go, which should be enough. So the next example it just wants you to find k, this natural number k, between 0 and 11, such that 39 to the power of 453 is congruent to k mod 12. And this is a huge power. Like if I wanted to, for example, let me actually just do this quick. Like if I wanted to just go and do a calculation with this, if the internet loads, let me pull over my screen. Yeah, so if I just plugged this power into a calculator, it likely won't give me much. Oh, I was doing something with it's like the default thing there. Okay. So what was it? It was 39 to the power of 453. And that's undefined. Like if you wanted to use a calculator, you couldn't even solve this problem. But using this trick that the book explains, or kind of leads you to finding, this actually becomes a lot simpler of a problem. So the first thing to do is realize that 39 to the power of 453 is congruent to 3 to the power of 453, mod 12. And that's because, I didn't need a parentheses there. And that's basically because 3 times 12 equals 36, and 39 minus 3 equals 36. Additionally, we can break down 453 as a sum of powers of 2. And the way we can do this is just subtracting. I already did this earlier, so I'll just show you quickly. 256, and then it subtracts and it gets to have 197, and then that gets to subtract 128, gets us to 69, and then subtract 64, which is the next power of 2 that can be subtracted. You get down to 5. You can't subtract 32, can't subtract 16, can't subtract 8, so then you subtract 4, 1, and then that 1 is all that's left. So you just add a 2 to the power of 0, basically. So you can write this as 256 plus 128 plus 64 plus 4 plus 1. And if we wrote this out in powers of 2, be 2 to the 8 plus 2 to the 7 plus 2 to the 6 plus 2 squared plus 2 to the 0. And the next thing that you do, you start figuring out what happens. So essentially what happens now, we realize that 39 to the power of 453 is congruent to 3 to the power of 453. Which ultimately becomes congruent if we break out this exponent to 3 to the power of 2 to the 8 times 3 to the power of 2 to the 7 times 3 to the power of 2 to the 6 times 3 to the power of 2 squared times 3 to the power of 2 to the 0. And what makes this useful is that essentially what we can do is just take 3 squared, or 3 to the power of 2 to the 0, and then you square it again, and then you solve it to a reduced form mod 12, and then you square it again, and that gives you 3 to the 2 squared. Square it again gives you 3 to the 2 cubed. So you keep squaring it, and it keeps going up to another number in this power series, in this in these different powers of 2. So let's kind of see how this works. So 3 to the power of 2 to the 0 is literally just 3 to the 1. So it's 3 mod 12. But then if we wanted to take 3 to the power of 2 to the 1, it would literally just be 3 to the power of 2 to the 0, and then we square it, because you just multiply by another 2. So it's literally just 3 squared, which equals 9, which ultimately is congruent to negative 3 mod 12. And the next thing that we can do is take 3 to the 2 squared, which once again is congruent to negative 3, the power before, 3 to the 2 to the 1, and then you square that. Well, this is congruent to 9, which once again is congruent to negative 3 mod 12. Similarly, you can do this again, 3 to the 2 cubed, and that is just, once again, negative 3 to the 2 squared. And negative 3 to the 2 squared, I'm just writing it out a little more explicitly this time, just so you can kind of see what's happening. And negative 3 to the 2 squared, as we saw, is congruent to negative 3. So negative 3 squared again, 9, which is equal to, congruent to negative 3 mod 12. And actually, you might be starting to see a little pattern here. Like each time we square it now, it's just going to continue to give us negative 3. And you can keep doing this process if you want, and you'll soon realize that you just keep squaring negative 3. So you find that besides 3 to the 2 to the 0 just being equal to 3, all these other ones are going to be negative 3. So yeah, you continue on, you find that out. So that means that 39 to the power of 453 is congruent to, and you just go one by one. So 3 to the 2 to the 8, that's going to be negative 3. 3 to the 2 to the 7 is just going to be negative 3. Same with 3 to the 2 to the 6, negative 3. And then 3 to the 2 squared is negative 3. And then 3 to the 2 to the 0, remember this one was slightly different, is just 3. And what this shows us, so all these negatives will cancel out, so it's negative, then positive, then negative, then positive. So it'll end up just being 3 to the power of 5. And 3 to the power of 5 just becomes 3 to the power of 2 squared, 3 to the power of 2, 2 to the 0, which becomes, it becomes this negative 3 and 3. And then I'll start a new line here. So then 39 to the 453 is congruent to negative 3 times 3, which is negative 9, which is congruent to 3 mod 12. So what we ultimately see is 39 to the power of 453, whatever this number is, it's some massive number. But what we know about it is congruent to 3 mod 12. Okay, so I might have gone a little bit fast here, but I think like what's ultimately useful about this method of breaking this power down into these smaller pieces here, into these powers of 2, it means basically that you can write this insanely large power of a potentially very large number. You can in modular arithmetic, you can write it as this product of just very simple integers, which can get you to this very simple number between 0 and the number you're taking the mod of. And this gives us a very computationally efficient way to do this. And it also helps point, like, given that it's a very computationally efficient way, it actually is very useful in different computer calculating contexts. Like if a computer needs to calculate a very large power, which is actually done a lot in cryptography, which we'll get into much later in this series, but it gives us a more computationally efficient way of breaking these down. And actually, if you know anything much about computers, like you'll know this is very similar to the way we break numbers down to create binary code. But yeah, just to see that, like, this is very computationally efficient compared to just trying to calculate this number straight up. And ultimately, like, using powers of numbers like in modular arithmetic can actually give us insights, as we'll see later on, into more complicated things within number theory. But yeah, so that's that for powers. Hopefully that this example helped, and you can see kind of how modular arithmetic can be used to help you take large powers of things and get information about those large powers in modular arithmetic. So the next topic that we're going to discuss is that of polynomials. So this, we're kind of expanding. So before we talked about addition, subtraction, multiplication, powers. Next, what we're going to go over, putting all of that together, we're going to start talking about polynomials in modular arithmetic. We're going to start by discussing them in modular arithmetic, and then we're going to go into some general principles about polynomials and some interesting proofs that start to eventually connect with modular arithmetic and with prime numbers, or with primality. It's a proof about composite numbers. So for the first thing that we're going to do, we're going to prove theorem 3.8. And this theorem states, suppose f of x equals a(n) xn plus a(n) minus 1 xn minus 1 plus ... plus a0 is a polynomial of degree n greater than 0 with integer coefficients. So then we're going to let a, b, and m be integers with m greater than 0. Ooh, that is a weird m. So then what the theorem states is if A is congruent to B mod m, then f of A is congruent with f of B mod m. And now for our proof, we're going to start just defining the terms again. So what this is basically showing is if you have two numbers that are congruent mod m, the function, their polynomial result, is also going to be congruent mod m. So you can apply all of these additions and multiplications and exponentiations, and the function is the result will be the same if the two numbers are congruent mod m, or the result will be congruent. So essentially all we're going to do is just very quickly spell this out, just using some of what we saw before. So f of x equals a n x n plus a n minus 1 x n minus 1 plus dot 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 plus a 0 is a polynomial of degree n greater than 0 with integer coefficients. Okay. Now we're going to let a, b, and m all be integers with m greater than 0, such that a is congruent to b mod m. Okay, so then by theorem 1.18, and remember this is the theorem about the powers in modular arithmetic, a to the I is congruent to b to the I mod m for all I in the set and then by theorem 1.9, oh yeah, reflexivity, AI is congruent to AI mod m. I don't know, I just want to use this theorem at some point. I feel like nobody ever uses reflexivity in a proof because it's so obvious. But it does make the statement a little bit more explicit later on. So like it's a more similar formulation to the actual statement of theorem 1.14. So by theorem 1.14, AI times a to the power of I don't know why in the statement of the theorem they have a twice. It makes it a little confusing, but a subscript I is different than a. It's not a type of a, they're completely different. B to the I. A is an input into the function, and a subscript is a subscript I is a coefficient in the function. Mod m for all I n. Okay. And then the last one that we're going to cite is by theorem 1.12, and this is just writing stuff out. So a to the n plus a n minus 1 a to the n minus 1 plus dot 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 plus a 0 is congruent to a n b to the n plus a n minus 1 b n minus 1 plus dot 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 plus a 0 for all. And this is essentially what we were trying to prove. Just trying to show that like changing the input to a different number that's congruent doesn't change the result of the function at all. So hence, this side is f of a. F of a is equivalent to, or is congruent to, f of b. Here, mod m. And that was all we were trying to show. Let me get rid of those parentheses. I had this bad habit of adding parentheses around this stuff in college, which you really don't need to do. I kind of realized upon thinking about it more. So then that is the proof. So this kind of gives us a baseline into kind of what polynomials can do in modular arithmetic. Like it's very similar to these type of like very introductory baseline theorems, just kind of putting them together and showing how they apply to polynomials. Basically just showing us like, hey, we can do all these operations in here, and then ultimately, like when we bring it together in the form of a polynomial, it doesn't impact the result. It doesn't impact for any of these operations, shouldn't impact polynomials either. Just kind of explicitly writing that out and proving that there. Now, one thing that you might remember is earlier we proved in theorem 1.21, which is now corollary. They prove it again here, which I'm not going to do, but I'll prove another one. We proved earlier implicitly using this theorem, but just kind of using all the building blocks like we did in this proof. We've previously proved that a natural number, which is the divisibility rule for 3, a natural number that is expressed in base 10 is, and base 10 is just how we typically write numbers, is divisible by 3 if and only if the sum of its digits is divisible. So like divisible by 3. So like the very basic divisibility trick you learn for 3. Add up the sum of their digits. If that's divisible by 3, then the whole number is divisible by 3. We proved that a lot earlier, like when we initially introduced modular arithmetic. Very much just implicitly kind of using this theorem, but instead of using it all together, we just kind of use the individual pieces that we had proved before. But now I want to show a proof of the divisibility by 9 rule here, which is a very similar rule, or it's another corollary. This is the one that comes before. So the corollary is let the natural number and be expressed in base 10 as n equals a k minus 1 ... a1 a0, and then let m equal ak plus ak minus 1 plus ... a1 plus a0. Then 9 divides n if and only if 9 divides m. Very simple. Okay. The type of thing that you remember from like elementary school. But the proof, so we're going to let m, and we're going to use this theorem that we just proved to basically prove this trick that we would have used like back in elementary. Let m and n be naturals such that n is expressed in base 10, blah, blah, blah. Just kind of restating the corollary stuff here, just defining the terms. In base 10 as n equals a k minus 1, dot, 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 a1, a0. And m equals a k plus a k minus 1 plus dot, 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 plus a1 plus a0. Thus, what this means, n equals 10 to the k, a k, plus 10 to the k minus 1, a k minus 1, plus dot, 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 plus a to the 1 times 10, plus a to the 0. And that's just what it means to be expressed in base 10. It'd be like that formula for just breaking out all of the digits into different parts of a sum. Now, since 1 is congruent to 10 mod 9, n equals a to the k, or a is congruent to 1 to the k, a to the k, plus 1 to the k minus 1, a to the k minus 1, plus a1 times 1 plus a0. And all of this just becomes, is congruent to ak plus ak minus 1 plus a1, or sorry, plus dot, 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 plus a1 plus a0, which is just congruent to m mod 9. So basically n is congruent to m mod 9. And now that we know that, we can just prove each direction very quickly. Suppose 9 divides n, so n is congruent to 0 mod 9. Thus, m is congruent to 0 mod 9. I don't know why I'm writing my m's like that. M is congruent to 0 mod 9. So 9 divides m. So that's one direction, and the other direction basically looks the exact same. Suppose 9 divides m, so m is congruent to 0 mod 9. Thus, m is congruent to, or sorry, thus n is congruent to 0 because m equals n. And this is actually by theorem 1.11, transitivity. So 9 divides n. Nice. Okay, so that is the rule for figuring out like what is divisible by 9. Basically, all you have to do is sum up the digits, and then you know that, and if that number that the sum of the digits is divisible by 9, then the number is divisible by 9. So like 81, for example, 81 is divisible by 9. 8 plus 1 equals 9. 9 is divisible by 9. Therefore, 81 is divisible by 9. Yeah, so that is that corollary. You would have learned that. like very early on in school, just with divisibility stuff. But now we actually have a proof for it, now that we're looking into kind of the higher level math behind these, behind modular arithmetic. We're kind of seeing behind the scenes like why this actually works, and it all has to do with modular arithmetic. But so this gives us kind of a basic knowledge about how polynomials function in modular arithmetic. But I think it's important now as well, or as the book does, to kind of step back and prove some useful theorems about polynomials that we're going to use all throughout the rest of our course. So very specifically, we're going to show, as the book says it, every polynomial gets large, and then later we're going to make a connection between polynomials and primes. So what exactly do I mean by saying that every polynomial gets large? Essentially, what we're going to prove is first that for every polynomial, we can choose some integer. So for every polynomial where the first term, the coefficient, is a positive number, we can find some integer where every number above it is also going to be positive. And then similarly, we can extend that to find any m, any number that once you choose some number eventually, every single result of that polynomial with an input above that number will get larger and larger. Basically what it's saying is the infinite behavior, like the behavior as it approaches infinity, is determined by that first coefficient. That first coefficient is going to overpower the rest. And sort of more of that's like kind of the calculus understanding once we get into limits. But what we're going to do here is actually prove this without using limits, just kind of looking at the algebra behind the polynomials. So let's actually get into this. Maybe when I state this more explicitly, it'll make a little more sense. So theorem 3.11, suppose f of x equals a n x to the n plus ... I'll write another term. I don't need to be lazy. A to the n minus 1, x to the n minus 1, plus plus ... a0 is a polynomial of degree n greater than 0, and suppose a to the n is greater than 0, then there is an integer k such that if x is greater than k, then f of x is greater than 0. So yeah, basically we choose some integer k, and now any x above that integer, any other integer that we choose that's above it, has to produce a result of the function of the polynomial that is greater than 0. Okay, so let's go into the proof here. And this proof actually took me a long time to really work on and actually create it in a way that makes sense, because there's so many little nuances, ways that you could go wrong. I actually looked back at my college notes on this particular part of the course, and I had two proofs written down. One was my own that I came up with, and then one was one that was come up with in class. And both of them were essentially right, but there were little issues that I've noticed upon reading it the second time, things that didn't actually work, but things were tended to be on the right track. So I put those together, and it was gonna be a very long proof, but I was working on it. I figured out a way to make it a little bit more concise and have it flow in a way that makes a little more sense. So hopefully this makes sense for you guys. It took me a while actually on this proof, a lot longer than I expected. But I tried to make it a little bit more concise and have it make a little bit more sense. But I ultimately think it is a lot clearer and more concise now than it was previously. And once you see it, you're gonna be like, why? How is this that hard to come up with it? It's a relatively straightforward proof, but there's stuff with like absolute values and ceilings and x needing to be greater than 1. That was just, you'll see as we get into the proof. But there's a lot of like weird conditions happening, and it ends up being very clean in this particular proof, but it was not that way before. So let f of x equal, and I'm going to use the summation notation a lot through the rest of this video because I don't want to write out the whole polynomial statement every time, just so I don't run out of paper space, and also because it takes forever. Where n, ai, and x are all integers such that a n is greater than 0 and n is greater than 0. Because also if a n is equal to 0, like then n would have to go down 1, because then you just have a 0 term. It's zeros at that term. But so what we're going to do first, we're going to note that if x is greater than or equal to 1, this sum n minus 1 I equals 0 a I x to the I is greater than or equal to the negative absolute value of itself. So you take the absolute value, take the negative. So every number, like whether it's, so this number, so the problem with this, like the AIs besides an could be either negative or positive. But what we're saying in the proof is essentially eventually that an will overpower it because of the x to the power of n. But so each of these terms, like this could be positive or negative. So I need to take the absolute value of this and make it negative. And then we know that if this is the negative side, it's equal to that negative absolute value. But if it's equal to the positive side, then it's larger than it. So essentially, this inequality will hold. Now the next point, x is positive. So since x is positive, it doesn't need this absolute value term on each of it, so we can essentially just look at the absolute value of these AIs, and it has to be greater than this negative of that sum of those AIs, because, for example, if one of the AIs is negative, that other negative will cancel it out, it'll be more positive, or possibly the other way around, or no, that's right. So it'll become more positive. So this always has to be greater than or equal to this sum. And this works because these x's are always positive, and then the time when these would be equal is if these AIs are always positive, but and that would be as low as it could possibly go, and that would mean that this second term here is as low as it could possibly be, and then it ends up equaling this. But so this basically makes them all positive. You add all these positives and make it negative, it gets lower and lower. So this second term, its floor has to be, or the lowest it could possibly be, is when all these AIs are positive, and then it would ultimately be equal to this negative sum. Otherwise, the second a negative term gets added in there, it makes the total a lot smaller, which when negated makes it larger. So that is kind of how that inequality works. And And then this has to be greater than or equal to negative. And this is where the fact that n is greater than or equal to 1 comes into play. Oh. To the n minus 1. So because x is greater than or equal to 1, x to the n minus 1 is always going to be larger than x to any power lower than it. All the other powers are lower than x to the n minus 1, so this x to the n minus 1 will be larger than each of those smaller powers, which when negated ultimately makes it smaller, which means that it will always be less than or equal to this. The only way it would be equal is if x is actually equal to 1, and then all of these are equivalent. So that's essentially that. So that's this inequality, and this is kind of the crucial set of inequalities for proving the rest of this theorem. So now we have this. So now what we can do is look at the polynomial equation as a whole. So hence, if x is greater than or equal to 1, f of x equals sum n I equals 0 a I x to the I, which is what we showed before, which is kind of how we wrote it out before. And now what we're going to do is take out the first term and add on the rest of it. And this is also explains why it's important that we're taking the negated portion, because otherwise the problem I was running into before, like I could get all the less than or equal to's. The problem was like flipping it, making it all the greater than or equal to's with that absolute value there. So now what we have is that f of x, if x is greater than or equal to 1, must be greater than or equal to, right? Yes, it must be greater than or equal to a n x to the n minus, see, because we're switching from positive to negative, minus this sum, n minus 1, I equals 0. And then ai, the absolute value of ai is to the n, x to the n minus 1. Which ultimately, it means that f of x, we're going to factor some stuff out. If x is greater than or equal to 1, f of x must be greater than or equal to x to the n minus 1 times a n x minus this. Now what this means, so basically what we're concerned about here is whether f of x is greater than 0 or not. And what this means, thus, so what we can do is look at this term, because this is always going to be positive. So what would it take to get this term to 0? This second term right here. So we need that term to be greater than 0. And this is greater than 0 when x is greater than 1 over a n sum n minus 1 I equals 0 a I. So this essentially constructs for us this term where if x is greater than this term, then f of x would be greater than 0, because this x to the n minus 1 would be greater than 0, and this term is greater than 0, so f of x must always be greater than 0 when x is larger than this. But additionally, we need to keep in mind that x has to be greater than or equal to 1. So x has to be greater than this term and greater than or equal to 1. So basically, we'll write this out. If x is greater than or equal to 1 and x is greater than 1 over a n, and the sum of n minus 1, I equals 1, ai, then f of x is greater than 0. So we're essentially there. Now what we have to do, so note that the proof says we need to construct a k where if x is greater than k, f of x is greater than 0. So how do we do that? Because right now we have two different expressions for x, and those two together show that f can be greater than 0. Well, what we do now, we can construct this k. So what we're going to do, we're going to construct k so that k meets these conditions and is an integer. So what we're going to do, we're going to let k equal the max. So k has to be greater than both of these numbers of the ceiling of 1 over a to the n. And this ensures that k is an integer. We need both terms in this max function to be an integer. And it's possible that some of these AIs are not integers. Or I guess it's possible that once you divide it, it's not an integer anymore. Because technically we did define all the AIs as integers, but once you divide by this an, it's not an integer anymore. So k is the max of these two. And what this does is ensure, so k is an integer, k is greater than or equal to 1, and k is greater than or equal to 1 over a to the n times the sum n minus 1, I equals 0. Sorry, I should have wrote 0 here. I don't know why I did that. I equals 0. Did I write it like, no, I wrote 0 in my notes, but k is greater than or equal to this. Okay, so we have this. So, and this is actually the final line, so we do have room. So if x is greater than k, x is greater than 1, and x is greater than this sum. Which implies f of x is greater than 0. And that is our proof. So what did we just do here? Essentially, the way this proof flows, we're trying to construct a k where if x is greater than that k, the function is always greater than 0. So what we did here is show what the conditions of a k would need to be, or under what conditions x would produce an f of x that's larger than 0 all the time. So we know that if x is greater than 1 and x is greater than 1 over a sub n times the sum from 0 to n minus 1 of the absolute value of a sub I, then we know that f of x will always be greater than 0. So if both of these conditions hold, f of x will be greater than 0. So we constructed a k such that this k is equal to this lower boundary where both of these conditions hold. or the k is the first integer above this lower boundary where both of these conditions hold. So that means any x that's above that is going to have both of these conditions hold and thus produce an f of x that is greater than 0. So hopefully that makes sense. And that's essentially what this proof is showing here. It's showing that there's this k that exists, and we can find it. We can explain what it is once we have this function. And we can always find this k that produces this lower boundary where if x is larger than it, the function is always greater than 0. Okay, so that's the first proof. And now what we're going to do in the second proof, it's going to be a little bit simpler, a little bit less conceptually complex, but what we're going to do now is expand this to make this lower bound not only to show that you can find an x, or can find a lower bound k where all x above it produces a function result that is greater than 0. We're going to change that to producing a function result greater than m, where we can choose any integer, any integer, and then from that we can always show that there is some k lower boundary where every x produces a function result that is above that that number m, that integer m. So let's write that out, and it's a bit of an expansion on what we were doing before. So theorem. Oh, actually, did you guys see the end of that last theorem? I wonder if my face block stuff. I guess not horribly. Okay. Because sometimes when I'm using the full screen, I need to be careful about that. So theorem 3.12. I don't want to prove theorem 3.11 again in this video. Suppose f of x equals a n x to the power of n plus a n minus 1 x to the power of n minus 1 plus dot 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 plus a to the 0, or a sub 0, is a polynomial of degree n and suppose a sub n is greater than 0. Then for any number m, there's an integer k which depends on m, such that if x is greater than k, then f of x is greater than m. Okay, so for our proof, we're going to let f of x equal the sum of n, I equals 0, a I x to the I, and then such that n, a I, and x are all integers. I guess I don't technically need to define it like that because the proof doesn't do that. Let me just say be a polynomial where a sub n is greater than 0. I'll start using that as my first line. And then we're going to let m be an integer. Or I guess it says for any number m. So I can just say let m be a real number. Now what we're going to do is let f star of x equal f of x minus m, which just equals, just to write this out more explicitly, sum of n I equals 1, and that was intentional this time, ai xi minus a0 or plus a0 minus m. Let's make my plus sign a little bit more plus-like. Okay. Now, since, let's scroll a little bit here. So since f of x, f star of x, is a polynomial of degree n greater than 0 and a n is greater than 0 for some k that's an integer, x greater than k implies that f star of x is greater than 0 by theorem 3.11, by what we just proved. Okay, so that's that part of the proof. So then thus, if x is greater than k, f of x minus m is greater than 0, so f of x is greater than m. So this is a very simple proof. It's a very quick expansion, honestly. We just had to construct another polynomial and know that that polynomial follows theorem 3.11. All we got to do is add that m there, or subtract the m there, and then that shows by essentially theorem 3.11 that we can make that polynomial be, or we construct this new polynomial, make it greater than 0, and as long as it's greater than 0, the original polynomial is necessarily going to be greater than m. Okay, so then the last theorem that we're going to do is a little bit different. So these first two were basically showing that, working together essentially to show that if you have any polynomial, you can always find some integer where an x, for all numbers that are above it, produce a value out of the function that's above whatever integer you desire. So you can always find that number. But this one's going to be a little bit different. We're going to prove something about polynomials and the primality essentially of their results. And what we can prove here suppose f of x equals a n x to the power of n plus a n minus 1 x n minus 1 plus dot 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 plus a0 is a polynomial of degree n greater than 0 with integer coefficient. Oh, weird. I see now. Coefficients. Then f of x is a composite number for infinitely many integers x. So this basically shows that we have a polynomial. Out of that polynomial, we can produce infinitely many composite numbers. Regardless of what the polynomial is, there will be the ability to produce an infinite number of composite numbers from it. So let's see how this works. So let's go into the proof. So we're going to let f of x equal the sum n I equals 0 ai xi, where n ai, because it says it with integer coefficients this time, and x are all integers, and n is greater than 0. So we're going to start by saying, without loss of generality, assume a to the n is greater than 0. Because if a n equals 0, use a n minus 1 as first term. And if a n is less than 0, use negative f of x. We can just negate the function and do the same thing, essentially. So by the theorem we just proved, theorem 3.12 or 3.12, I guess I call it theorem 312. It's not really a point. It's not a decimal. If x is greater than k, f of x is greater than 1 for some integer k. And now we're going to let q be the result of the function when you plug in k plus 1. So q is an integer. Let's just list facts we know about q. Q is an integer. Q is greater than 1. And f of k plus 1 is congruent to 0 mod q. So those are the facts we know about q right now. Another thing to note, just by how divisibility works with congruence, LQ is congruent to 0 mod q for all L in the natural number system. Thus, by theorem 1.12, which is the additive principle, k plus 1 is equivalent to k plus 1 plus LQ mod q for all L in the naturals. This is because you're essentially just adding these numbers together. You're adding k plus 1 plus 0. That's the same as k plus 1 plus LQ, which is 0. Now, one thing to note here is that k plus 1 isn't necessarily equivalent to 0 mod q. But what we know is that k plus 1 is equivalent or is congruent to k plus 1 plus LQ mod q all the time, every time. But k plus 1, we don't know anything about its actual equivalence in mod q. We know, or its actual congruence in mod q. But we do know that when you plug k plus 1 into the polynomial, it produces 0 mod q. Okay, so then yeah, okay. So then where is this? Therefore, by theorem 3.8, f of k plus 1 plus lq is congruent to f of k plus 1. It's congruent to 0 mod q. Now, this means, thus, q divides f k plus 1 plus lq for all L congruent to n. So now we have this, what looks like an infinite list of numbers resulting from it. But what makes this crucial is what we proved in theorem 3.12. So we know that for all x greater than k, everything that you plug in greater than k, the function's result has to be greater than 1. So q has to be greater than 1, which means q dividing this shows that all of these numbers are actually composite. None of them are prime. Additionally, since the list of natural numbers is infinite, this is an infinite list. So let's write this out explicitly. A equal to the set plus LQ, where L is a natural, defines an infinite set of integers where f of x is divisible by q and therefore composite, since q is greater than 1 for all x in A. Okay, and that completes that last proof there. Essentially what we're showing here is that for any polynomial, we know that there is an infinite number of results of that polynomial, of that function, that are composite. There's going to be an infinite number of integers, and it's defined by this set that we defined, where A has to have a cardinality of an infinite cardinality because the cardinality of the natural numbers is infinite. So with that, that's all for this video, all for this episode. And we finally made it to 10 episodes in this number theory series, but somehow we're barely scratching the surface of this textbook. But we're really getting into it now. We're starting to get into more interesting stuff, starting to get into more interesting and complicated proofs. But I think with so much to go, I really hope you guys stick around and are excited to watch the next episode and keep going on this number theory journey. But with that, if you liked the video, feel free, go down, hit the like button. If you really enjoyed it, there's a subscribe button if you want to keep being notified of these videos. And if you enjoyed the video so much that you want to give me money, I don't know why you would, but I would appreciate it if you go to the Patreon below and support down there. Additionally, there is a Discord down below if you want to go ask questions. I have a Discord community, very small, and not many people talking yet, but I'll check Discord occasionally if there's anything in that server. But with all that aside, I want to thank you all for watching, and I hope to see you all in the next video. Peace.